Thank you for joining us for the HPL seminar on a snowy, sad, gloomy day today. Hopefully this will make it a lot better and worth it. So today it is my pleasure to introduce our speaker, By.L.Cozma, who is currently a second-year master's student in kinesiology, specializing in biomechanics. She is co-supervised by Dr. Brent Edwards and Dr. Jared Fletcher, and she previously completed her Bachelor of Science degree also here in kinesiology, with a major in exercise physiology in 2024. Her research is focused on trying to understand why energy cost increases during running when joint work is redistributed. Outside the lab, Lisa is a track and field athlete, and although she's completed her university eligibility, she continues to compete at the national level in long jump, which is pretty impressive. And in a bit of an irony, despite being a track athlete, she admits that she does not actually enjoy running as much as people would expect her to. Today, she will be presenting her work titled The Influence of Mechanical and Muscle Efficiency on the Increasing Energy Costs Seen with Joint Work Redistribution. Thank you, Lisa.
Awesome. Thanks, Ashna. Hopefully everyone can hear me okay. If not, I'll just talk louder. So energy cost is the main determinant of endurance running performance. A lower energy cost is associated with faster performance times. And this whole body energy cost is largely dictated by that of the muscles contributing to moving the body during running. And this is based on the muscle length and muscle shortening velocity. It is based on the magnitude of force production of the muscle, and it is also based on muscle fiber type. Shown to us in this graph by Buchner et al. In 1991, who did a distance running study over 60 kilometers with the distance in kilometers on the x-axis and the whole body energy cost on the y-axis. You can see that throughout the course of the run, energy cost does increase about 7 to 8%. Mechanical work is performed by the joints to displace the body from point A to point B. And this mechanical work obviously comes at an energetic cost. We also know that total lower leg mechanical work is not distributed evenly between the three joints of the lower leg, being the ankle, the knee, and the hip. And we also know from previous studies done by Sano and Sequoia that over the period of a 10-kilometer run, this joint work is then also redistributed unevenly with a decrease in ankle joint work throughout the course of the 10-kilometer run and an increase in knee and hip work over the course of this 10-kilometer run. This joint work redistribution is thought to be the reason for this increase in energy cost that we see during running. And the main hypothesis and thinking behind this is that it is believed that the ankle is a more efficient joint than the knee. So what this means is that for a given amount of work, the ankle energy cost is going to be lower than that of the knee. So when joint work gets redistributed from the ankle towards more proximal joints, such as the knee and the hip, consequently, the energy cost will then increase. However, this theory has not been directly tested, and we do not know if there is a direct relationship between the two. The ankle is presumed to be a more mechanically efficient joint because of three main points. So first of all, there is a greater potential for elastic strain energy return from the Achilles tendon compared to the patellar tendon, and that is because the muscle tendon unit of the plantar flexors have a long Achilles tendon with a short muscle belly, but for the knee extensors, you have a very short patellar tendon with a large muscle mass. Secondly, it is believed to have a greater plantar flexor efficiency compared to the knee extensors due to the muscle size and architecture. So the plantar flexors being a smaller muscle mass with sarcomeres arranged in series that have a lower energy cost than the large muscle mass of the knee extensors who have sarcomeres arranged in parallel. And lastly, muscle shortening velocity associated with running is more closely associated to the optimal shortening velocity of the plantar flexor muscles, which are a type 1 oxidative slow twitch fiber, compared to the knee extensors, which are a type 2 glycolytic fast twitch fiber. And when we run prolonged distances, we tend to run at fastest shortening velocities associated with that of these slow twitch unflexible muscles. And this is depicted to us in this Barkley study that was done on mouse muscles, where we have the soleus being a more of a slow twitch muscle fiber, and the extensor digitorum longus in the bold black curve, which is more of a fast twitch muscle fiber in mice. And you can see here that optimum mechanical efficiency or optimum energy is more closely associated with slower shortening velocities of slow twitch muscle fibers. So this kind of raises us the question, is there a direct relationship between this increase in energy cost that we see with prolonged running that was shown to us in the Buchner et al. Study over 60 kilometers, and this joint work redistribution that was shown to us by Sano? And you can see this here, that the black triangles represent the ankle joint work that is decreasing with prolonged running, and the black squares and black circles represent the knee and hip work that is increasing with prolonged running. Therefore, the purpose of my study is then to determine the energy cost to perform a fixed amount of work at the ankle and at the knee joint, and subsequently to then compare the mechanical efficiency and also the muscle efficiency of the individual muscles that contribute to joint movement when performing that fixed amount of work. And these two underlying questions would then help us answer our overarching question of if mechanical efficiency can actually explain the elevated energy cost seen with prolonged running because of our joint work distribution hypothesis. For this study, I hypothesized that yes, the ankle joint and yes, the plantar flexor muscles will demonstrate both higher mechanical and muscle efficiency compared to the knee extensors and the knee joints, subsequently confirming our joint work redistribution hypothesis relating to increased energy costs seen with running. For the methodology of this study, I recruited 13 participants, both male and female, together, and they came into the lab in one testing session and they performed 3 different tests. The first one is we performed a maximum voluntary contraction on the dynamometer at the ankle joint and at the knee joint to determine a 50% target torque at the ankle, which we will then use in the joint work condition. Then our participants performed isokinetic contractions at 6 different angular velocities, both at the ankle joint and at the knee joint. And this was for us to determine the force velocity relationship at the joint level using angular displacement, and at the muscle fascicle level using our fascicle displacements. From here, we were able to calculate a power velocity curve following an efficiency velocity curve, which I will explain later on when we go through the results. And lastly, our participants performed one joint work condition, which I termed 50-50. And in this joint work condition, participants performed 120 cyclical contractions at the ankle joint or at the knee joint at a frequency of 0.5 hertz with a target torque of 50% of ankle maximum voluntary contraction that we gathered from our MVCs earlier, and 50% of joint specific range of motion. So then that means that overall our participants performed relative amounts of work between the ankle joint and the knee joint. The instrumentation for the study, we had our participants sitting in dynamometer, where we directly measured the torque and the cyclical contractions. Our participants also had a VO2 mask on, measured by the metabolic cart, where we gathered VO2 and VCO2 data. And then lastly, our participants had 2 ultrasounds strapped on, one at the gastrocnemius medialis and the other at the vastus lateralis, where we were able to look at fascicle length changes and calculate muscle work from there. The way that we calculated muscle efficiency at the joint is we only looked at positive mechanical work. So this only means the work that the fascicles do to contract, not the work that they do in the eccentric plane of motion. So for here, when we're talking about joint mechanical efficiency, we're including all of the muscle tendon units that contribute to this joint motion. And we did this by multiplying the joint torque we got from the dynamometer by the angular displacement of the joint, and we divided this per the 120 cyclical contractions in the joint work condition. And then our energy cost, we gathered this from the metabolic data, which was our total body VO2 and VCO2. And then we plug this into a caloric equivalent of oxygen formula that gives us joules. And we also divided this by 120 cyclical contractions. So in the end, we end up with joules per cycle of positive mechanical work divided by joules per cycle of energy cost, which gives us efficiency in percent. Next, when we looked at muscle efficiency, this was specific to the gastrocnemius medialis for the plantar flexor muscles and the vastus lateralis for the knee extensor muscles. And for this one, we looked at the torque from the dynamometer and we divided this by the moment arm of the specific muscle. And then we multiplied this by the physiological cross-sectional area that this muscle occupies within the leg. Yeah, within the leg. Then we also multiplied this by the fascicle length changes that we gathered from the ultrasound. And we divided this per cycle again. So then we end up with positive joules of mechanical work. And the energy cost is again taken from the total VO2 and total VCO2, plugged into that caloric equivalent of oxygen formula, divided by our 120 cyclical contractions. And that is how we end up with joules of positive muscle work divided by joules of energy cost, which gives us muscle efficiency in percent. I just have a little video here to show you guys, and this hopefully would work. And you can see here how the plantar flexor muscles move accordingly to the ankle as you are doing ankle plantar flexion motions. And we essentially measured the distance at which the fascicles are contracting. Okay, awesome. So now, when we look at our results, we have some very exciting findings. And our first finding is when we look at mechanical efficiency, our knee joint actually showed significantly higher mechanical efficiency than our ankle joint. So then we have to go look at our muscle efficiency. And when we compare the gastrocnemius medialis muscle efficiency to the vastus lateralis muscle efficiency, we actually see that there is no significant difference between the efficiencies at the muscle level. So that kind of raises some questions for us. Why was the knee joint more mechanically efficient? Well, we know that joint mechanical work is driven by muscle mechanical work. Therefore, our answer definitely lies in how the fascicles are operating and how the fascicles are shortening. If you remember the sparkly graph that I showed you earlier, is a muscle mechanical efficiency on the y-axis compared to fascicle shortening velocity in V over V max. So what this means is V max is the fastest the fascicles are shortening based on Barclay's data collection. And it is expressed in percent from 0 to 100% of fascicle shortening. The soleus, being a more of a slow twitch muscle fiber, shows a peak efficiency associated with a slower shortening velocity. However, when we look at the extensor digitorum longus, also showing a relatively similar peak efficiency to the soleus. However, this efficiency happens to occur at faster shortening velocities, V over V max. So that means that our ankle and knee joints, being predominantly different muscle fiber types, obviously would have a similar curve to this. So the way that we calculate this efficiency velocity curve is from our isokinetic contractions at our 6 different angular velocities. From here, we are able to create a force velocity graph based on our fascicle shortenings, V over V max, and our fastest fascicle shortening was observed at our fastest angular displacement. And from here, we multiply force with displacement to get our power velocity graph. And what we notice here in our power velocity graph is that we have a peak power of the gastrocnemius in blue associated with a shortening velocity of about 0.36 V over V max. So 36% of maximum shortening velocity. And then we also notice the peak power of the vastus lateralis all the way up here is associated with a shortening velocity of 50% of maximum shortening velocity. So from here, we know that peak power is closely associated with peak efficiency. Therefore, we are able to create our muscle efficiency on the y-axis and fascicle shortening velocity V over V max on the x-axis. Again, the ankle efficiency velocity curve is in blue. The Vastus lateralis efficiency velocity curve is in red. And in blue, the light blue dot represents our GM shortening during our 50-50 joint work condition. And the pink dot on the red curve represents the vastus lateralis shortening velocity in our 50-50 condition. We notice two things on this curve. So even though the efficiency, the muscle efficiency between these two muscles was similar, the shortening velocity of the gastrus medialis is associated with a faster shortening velocity than peak efficiency at faster shortening velocity, even though the efficiency we noticed during our joint work trial is about 99% of what the calculated theoretical peak efficiency would be based on this study. Next, we notice that vastus lateralis over here is shortening at 0.35 V over V max, or 35% a maximum shortening velocity, while its peak shortening velocity is associated with 0.5 V over V max. So that means that we are shortening significantly slower than peak optimal efficiency, than the shortening velocity associated with peak optimal efficiency. So what does this graph kind of tell us? It tells us that if the vastus lateralis was shortening at an even faster shortening velocity during our condition, we could have achieved a higher total peak efficiency. However, in our gastrocnemius medialis, if we had shortened at a slower velocity, we could have achieved an overall potentially higher peak efficiency. But if we had shortened even slower during our joint work conditions, we could have achieved a higher ankle or a higher gastrocnemius medialis efficiency compared to the vastus lateralis efficiency. Therefore, when we look at our hypothesis of was the ankle joint work and was the ankle joint and was the plantar flexor muscle really more efficient than the knee and the knee extensor muscle? No, we will end up rejecting this hypothesis. And this is because saying that either the ankle or the knee is more efficient than the other is an oversimplification, because it clearly depends on where the fascicles are shortening on their efficiency velocity curve. And therefore, we will end up rejecting the proposed mechanism that joint work redistribution influences energy costs, because from this study that we found, the knee extensor, the knee joint was significantly more efficient than the ankle joint. So then a search for an explanation continues. We don't stop here. We're going to keep looking at our data and keep seeing what other important information there is. And one of the main, one of the main limitations from this study is that we looked at relative amounts of work instead of absolute amount of work. So this means that the knee joint overall did more work than the ankle joint. And we also know that efficiency is highly related to work. In previous cycling studies, where the RPM stays the same throughout different amounts of work, so work is represented by kg per minute on the x-axis and efficiency is on the y-axis. At different RPMs, we notice that efficiency decreases with increasing work rate. And when efficiency decreases, that means that energy cost increases. And you can notice that through different RPMs, this energy cost or this efficiency decreases at different rates. Therefore, we need to take a look at the relationship between energy cost and work that our joints are doing. So from here, we end up creating an energy cost per joules per cycle on the y-axis, and work also in joules per cycle on the x-axis between the ankle joint during our 50-50 condition and the knee joint during our 50-50 condition. And we notice here that the knee joint did significantly less work than the ankle joint, but its energy cost was also significantly lower than that of the ankle joint during our 50-50 condition. So how does this apply to, let's say, a hypothetical joint work redistribution scenario? So with a hypothetical of total leg work of 100 joules, this is distributed unevenly throughout the ankle and the knee, where we would have a hypothetical 52 joules of ankle work represented over here, and a hypothetical 29 joules of knee work represented over here. And we know that at 29 joules, the knee operates at about 7.25% efficient, and the ankle joint operates at 6.5% efficient. With joint work redistribution, we see that knee work increases and we see that ankle work decreases. And we also notice that our efficiency increases in the knee, but our efficiency decreases in the ankle. Another thing that we notice here is that there is a crossover point if we were to extend our trend line or our regression equation. And at this crossover point, it costs more energy to do work at the knee than it does to do work at the ankle. So this means that at some amount of low work, the ankle will actually express higher efficiency than the knee. So is the energy cost increase that we see during full-on running actually related to this joint work redistribution that we see? The answer could lie in what something is called delta efficiency. So what delta efficiency is the change of mechanical work with the change in energy cost. So it's essentially this energy cost and mechanical work relationship that we see. The slope of the line represents our efficiency. So we need to take a look at how our efficiency changes with increased or decreased amounts of work. In the first graph that I originally presented you, we looked at a hypothetical delta efficiency where we compared different amounts of work between different people. In this second study that I will present to you, that is preliminary research that I'm still analyzing at this moment, we are then looking at different amounts of work within one participant, and we are comparing this different amounts of work with other participants. So for this one, we had N of 11 participants come in, both male and female, and I've analyzed 7 participants, which I will show you today. And again, participants came in for one session in the lab where they performed maximum voluntary contractions at the ankle and at the knee. And this was to determine a variety of target torques for the joint work conditions. Next, our participants also performed the same isokinetic contractions at the 6 angular velocities for us to be able to create that muscle efficiency and fascicle shortening velocity curve. And lastly, our participants now performed 4 different joint work conditions with 30, 40, 50, and 60% of ankle maximum voluntary contraction torque and 50% of ankle range of motion. So now that means that we've restricted the range of motion to be the same angular displacement at the knee and at the ankle, and both joints now had the same target torque in 4 different conditions. So now we're able to compare absolute work at the ankle with absolute work at the knee. And this bar graph over here shows you the different conditions of 30, 40, 50, and 60% between the ankle in blue and the knee in red. And you can see here that there is no significant difference between the work done at the knee joint and the ankle joint between the trials, which means we did similar amounts of work. So we are now comparing absolute amounts of work, which is fantastic. So when we take a look at our mechanical efficiency, this probably seems like a lot to take in, but you have your 30% condition up here, your 40% condition over here, 50% and 60%, and we are comparing the knee to the ankle, or over here, the ankle to the knee. That's just how JASP spit out my results. But we only notice a significant difference in efficiency in the 30% condition, where the ankle now shows higher efficiency compared to the knee, and this is mechanical joint efficiency. So when we take a look at our mechanical joint efficiency with our work amounts on the x-axis, we notice a couple things from this graph. And first of all, when we look at the slope of the trend line between work and mechanical efficiency of the ankle in blue, we notice that it is relatively flat, which tells us that energy cost increases proportionately to the work done at the ankle joint. However, in the knee joint, we notice that it increases positively, which tells us that energy cost does not increase proportionately to the work done at the knee. The other thing that we notice is that there is this crossover point that occurs at about 35 joules per cycle. And this tells us that if we do less work than 35 joules per cycle on the dynamometer, the ankle shows higher efficiency than knee. But if we start to do more work than 35 joules per cycle on the dynamometer, we notice that then the knee efficiency is greater than that of ankle efficiency. So now looking at our delta efficiency relationship, which is the energy cost with our work, we have the blue data points showing the ankle joint and the red data points showing the knee joint. And we also notice that there is a crossover that happens in energy cost, where with lower amounts of work, the ankle shows higher efficiency or lower energy cost, and with higher amounts of work, the knee shows higher efficiency or lower energy cost. And when we apply the 4 joint work conditions that we did, 30, 40, 50, and 60%, we notice this same trend with only a significant difference at the 30% condition. Again, this is preliminary data with 7 participants, so it has not correctly been powered yet. So the overall take-home messages from both of the studies that I presented to you is that joint efficiency and muscle efficiency highly depends on shortening velocity. As you can see here, there is also a crossover point in the shortening velocity where we would expect higher gastrocnemius medialis efficiencies at slower shortened velocities and higher vastus lateralis efficiencies at faster shortening velocities, though overall peak efficiency seems to be higher at the knee seems to be higher in the vastus lateralis muscle, compared to the gastrocnemius muscle. Secondly, when we look at delta efficiency, lower work rates or lower work amounts seem to correspond to lower ankle energy costs and higher ankle efficiencies. And that is the truth for the opposite, where we see higher work amounts corresponding with lower knee energy costs and higher knee efficiency. But lastly, we need to remember that energy cost is what dictates performance, not necessarily efficiency. So this energy cost that we see during running needs to be optimized between all these joints to find a balance of which consumes the least amount of energy as we prolong the run. And overall, both of my studies do not confirm or deny the fact that joint work redistribution contributes to the increase in energy cost seen, because the work that we did here is solely on the dynamometer, and the work that is done during running is different than the work that is done on the dynamometer, and we can only make hypothetical assumptions about how joint work gets redistributed on the dynamometer versus during actual cyclical contractions we see during running. So the summary of both of my studies is that assuming that one joint is more efficient than the other is a gross oversimplification, and we really need to take a look at how the fascicles are shortening and where they're shortening on their efficiency velocity curves. And as always with studies, there's tons of limitations, but all the limitations mean that there are new avenues of studies for other researchers to hop on and explore. So the first one is I didn't even consider doing hip work during my study. And hip work contributes to lower limb energy costs, as you saw, between 19 and 23%. So that's a huge chunk of energy cost that we didn't consider during these studies. Secondly, we should probably consider the fascicle shortening velocities of the other muscles. As you know, for example, the plantar flexor muscles are not only comprised of the gastrocnemius medialis, there's the soleus and there's the gastrocnemius lateralis, and so many other muscles in there that probably have different efficiency shortening velocity relationships than the gastrocnemius medialis. And this all contributes together to overall joint efficiency. Next, we also need to take a look at tendon work. So muscle tendon units work together to move the joint. And we know that if the muscle has to do a lot of work, the tendon doesn't do as much work. But if the tendon does more work, the muscle then has to do less work. So clearly that also contributes to the muscle work that we see and the overall joint efficiency. Next, during running, there is also negative work. My studies only looked at positive work, so the work that the muscle fascicles are doing to contract, and negative work also consumes energy. So that is also another avenue of study that we need to look into. And lastly, we need to put all of this together and actually do a joint work redistribution study on a force instrumented treadmill with some kinematic motion capture analysis and direct whole body calorimetry. So we can really see if the relationship between joint work redistribution is actually related to the increased energy costs that we see during running. So I would like to thank the members of Faster Lab and the members of the Edwards Lab for their continuing support, and for EdCert and Sigma X for their funding for my studies. Thank you.
With that, the floor is open for questions. Who would like to start us off? Maria and then Mike.
Correct me if I'm wrong, but did you say you were only looking at concentric muscle contractions?
Yeah, so just the active contraction of the muscle.
Why did you not look at concentric as well? I'm curious.
Because I think on the dynamometer, it's quite hard to get eccentric motion because where it can regulate the angular displacement of the arm of the dynamometer in a concentric way, but not so much in the eccentric way.
Yes, I want to speculate, what do you think, how your results would change if you did do your testing during running? How would you want to
Oh, sure. So, the big thing, that's the difference between doing dynamometry studies and running studies, is that you can get way higher forces during running than you do on the dynamometer. And, in that sense, I would like to speculate that we would see this same trend when we have higher forces. So, for example, faster running speeds, we would see more work at the knee, which would reduce the energy cost. And with maybe slower speeds or slower running, we would see more work at the ankle, which would reduce the energy cost, and vice versa. But because of that, because the forces are so different and they're so high during running, I would like to see this relationship. And I also know that the tendons also function differently during running than on the dynamometer. So that's also a whole other thing that we need to consider. Yeah.
Aaron?
Now, I know this is contingent on speed, but do you have like an idea of the classical shortening velocity during running and the distance, like the contraction distance of the plantar flexors?
Yeah, so during running, the plantar flexor, so the Achilles tendon allows the plantar flexors to contract pretty isometrically because there's a huge strain in the tendon. So when the fascicles contract pretty isometrically, I don't think they contract very fast because they don't have a long way to go. So in that sense, you could possibly see a higher efficiency or lower energy cost of the plantar flexors because they're contracting more isometrically. If that sort of makes sense. Yeah.
I don't know about anything about physiology. But I think I know enough to be dangerous. So I feel like I remember learning about something called cardiac drift or something.
Oh, yeah.
The idea that you do the same amount of work, like on a bike, for example, and then over time you will see increases in the, I think, oxygen consumption. Heart rate goes up. And am I making sense?
Yeah.
Enough to be dangerous.
Yeah.
How much of that can explain this uptick in the metabolic cost of running over time?
Yeah. Okay, so this is me digging back deep into my physiology of undergrad with cardiac drift, and that has to do, I think, with the cardiac output over time, that the heart needs to pump more blood over time, and that could contribute to the energy cost. I don't quite remember what cardiac drift is in itself, but it is that the heart pumps more blood over time to continue doing the same amount of work or supplying the same amount of oxygen to the muscles, if I'm correct.
Would you see increases in metabolic costs on upwards of 7, 8, 9%? Or is it more like a 1% kind of thing?
Simply due to cardiac drift, yeah, probably not that much, right?
No,
Okay.
probably not.
Cardiac work's pretty small relative to the rest of the body.
Yeah.
Okay, all right, so it's not cardiac drift. Okay, so So the other question I have is, that finding of work redistribution from ankle to hip.
Hmm.
Is that a consistent finding? Is that just one study that showed that? Are there a million studies that showed that?
Yeah.
That's just a quick answer.
There's a couple of other studies that have shown that. I know, Sasha Sequoia did some running shoe studies here at the HPL on this and also found this redistribution of work in different running shoes.
Yeah, I question the, I question the ecological validity of that. I'm an author on the paper side.
Yeah.
I can question that. Okay. My question though is why is there then, if it's a consistent observation, why is there a redistribution of work? What happens at the ankle joint that necessitates you to do more work at the hip?
So, a big hypothesis in this is that because the plantar flexors do more work, than the knee extensors, they tend to fatigue faster. There has been other studies that have shown that, the plantar flexors can contribute up to 85% of total work, or they use up to 85% of their total, power when, running or something like that, and that significantly decreases over the course of the run. And that shows that plantar flexors fatigue over the course of the run. So if they fatigue, they now have to contract harder to produce the same amount of work. And this joint work, instead of contracting harder at the plantar flexors, which then costs probably more energy, it gets redistributed to less fatigued muscles, such as the knee extensors, who are able to contract to maintain that mechanical work at a lower energy cost, something like that.
How long was the run in the saddle paper?
10 kilometers.
Going that road?
Nice job. That was really good. Nice to see how it's all progressed since, a couple of years ago when we first chatted about what you were gonna be doing with Jared and Brent. Very cool. So the thing that stood out most to me is 120 reps at 50%
Yeah.
of your maximum MVC force. Did I have that right?
At the ankle.
Yeah, and so what was it at the knee then?
It was also 50%.
Yeah.
Yeah, so we use the same target torque at both of the joints.
So what, I mean, I was surprised because that seems pretty hard.
Yeah.
So walk me through what happened over the course of your 120 reps.
So we noticed that as the 120 reps progressed at the ankle, our participants had more and more trouble maintaining this torque,
Yeah,
which is probably why we see, I'm gonna call it an even bigger difference between, the relative amounts of work that they did. But at the knee, it was a lot easier for them to maintain that torque, and a lot of participants accidentally overshot this by a little bit too. So that also contributes to the differences that we see. And overall energy cost was also higher at the ankle to maintain this target torque compared to at the knee. So
and so when you do your calculations, you just sort of average over the 120, like so you take each cycle and.
yeah, so we take each cycle and then we only use the positive
Yeah.
torque from that. And then we take the integrals of all that positive
Yeah.
work and we end up with total work. And then we divide that by the 120 cyclical contractions. So then that's how we would end up with how much work was done for one contraction.
But is there any, I mean, I haven't really thought this through carefully, but is there any implication of having one muscle group over 120 contractions that's fatiguing a ton? The other one that's hanging in there pretty good,
Mhm.
does that influence at all, do you think? The dynamics that you're trying to see? So for example, if you looked at your repetitions over the first 30 versus the last 30, would you see a different relationship, do you think, than what your data currently shows?
Probably, I would argue like yes and no.
Yeah.
Because our 50% target torque was meant to be a sub-maximal torque that you could maintain for 120 cyclical contractions. Some of our participants did find it quite challenging.
Sure.
So I think you would probably see a numerical difference, but maybe not something necessarily statistical between the first half of the contractions and the second half of the contraction.
Right.
Yeah.
Do you think the behavior overall would stay the same regardless of whether you took the first 30, the last 30 versus the
the middle area.
The middle 30 and versus the whole thing.
Yeah, and I think if we really wanted to focus on that, we probably have to bring more participants in and study just this change in, I'm gonna say, target torques over the course of the 120 cycles of contractions, even though it was a submaximal torque that we thought they could maintain. You know what I mean?
I think we have an online question, then Aaron, then Jared.
Well, I just read off the question online here, say, how challenging was it to visualize vesicle of the vastus lateralis muscle? Could you see the whole muscle vesicle in the ultrasound?
Yeah, so I think I actually have a video of that somewhere in my presentation, but we had to adjust the depth that we used to view the image so we could get the whole length of fascicle. And I believe it was a depth between 40 and like 50 millimeters, something like that. And yes, we were able to see the whole fascicle length. And that's also because the probe that we used is like relatively long. So there's a pretty large image captured on the fascicle. So we're able to get the whole fascicle.
Will you tape the probe to the muscle?
Yeah, so we tape the long probe on the pennation angle of the fascicle so that we're able to see multiple of them and then measure how they change from their, I guess, ends.
Okay.
Yeah.
Thank you.
Aaron?
Did you take MVC at the end of the 120 cycles?
No, we didn't.
Okay, so I guess more theoretically.
Yeah.
Instead of having like a 50% torque per cycle.
Yeah.
Do you expect the same results if there was a consistent loss in MVC? So like if everyone lost 50%, regardless of how many cycles they went through.
Mhm.
Would you expect to see the same like joint work redistribution?
So you're saying that did we or did we not use the 50% torque? Sorry.
No, yeah, it doesn't.
Okay.
Let's say you use the 50% torque
Sure.
until they can't maintain that.
Yeah.
Would you expect to see the same results as 120 at your 50% torque? Because I'm assuming that MVC would change differently per person by the end of it.
Yeah, so I think we would see probably a significant increase in the energy cost with the amount of torques that we would do. And this is because we know that efficiency decreases with work over time. So then that would directly translate to an exponential increase in energy cost, regardless of the torque that they would keep. Because at some point you will fatigue and you won't be able to keep this torque. So you're going to, I'm gonna say, push less. And then your energy costs would continue to rise for that.
Jared, that question?
Not thinking about Aaron's question. Maybe just to follow up on Matt's question about the like analyzing the first 30 versus the whole 120 contractions. Do you remember why we couldn't or shouldn't analyze the first 30 contractions, especially when it comes to energy costs?
Yeah, because they didn't achieve a stable VO2 and VCO2 because it was still rising in the first couple of contractions. And we wanted to measure the contractions when the metabolic parameters were stable, which would tell us that they have a submaximal contraction exercise. Yeah.
So I guess, again, I'm gonna try to get this straight in my head. So let's say you're saying that the plantar flexors are not as efficient as the knee.
Yeah.
But if you're getting more tired at the ankle, and so they behave differently over 120.
Right.
So at 100, as you get to the last bit on the ankle, you're like
Yeah.
working like crazy.
Right.
Whereas with your knee extensors, you're all right.
Yeah.
Is that because the muscle is, like there's something there to do with the actual behavior of the muscle? Or is that just because the task was different, relatively speaking, for the knee and the ankle? Maybe I'm.
In other words, could the muscle work be different for the muscle shortening? Yeah, I guess it would be muscle work be different the last 10, 20, 30.
Yeah, like you drop off more at the ankle, so you're obviously working harder. Obviously to keep it up. whereas your knee's kind of in a good groove.
Yeah. And that's probably because, the knee. The target torque for the knee is significantly lower than that of the ankle compared to its maximum NBC.
I
Right?
think that's critical.
Yeah,
It's like you have the MBC of the knee.
Yeah.
Is probably way bigger than the MBC of the ankle.
yeah, I think it was.
Because you
over-
hold up musculature.
Yeah, I think it was about 100 more, like it was huge.
So you're doing 50% of your MBC at the ankle,
Yeah,
which is probably like 20% of the knee's MBC.
Yeah. yes,
Isn't the MVC like, don't you make them do it at the ankle and the knee, and then isn't that like relatively you're doing the same, or am I oversimplifying?
so the NBC is we did different degrees of range of motion where we had them push like as hard as they can. And the torque that was peak torque is your NBC, regardless of where you are at your, and your range of
Okay,
motion
so
is.
you're not taking your MVC that you did your like ankle plantar dorsiflexion in and then giving them 50% of that. And then the MVC that they were doing with knee flexion extension and then making them do 50% of that.
No, so we
It's
did,
that global, like the one MVC and then. 50.
yeah, it's the one NBC of the ankle that we achieved at the ankle that we did for the knee and the ankle. And then it was the range of motion, which was different.
Okay. Just see. Okay, that was-
So the idea would be to keep the total work the same.
Yeah,
right.
Because that's what's supposed to be happening in running.
Yeah.
If it's more or less efficient, you have to make the work the same.
So why not do the experiment in a way where you have your relative percentages that you know are what is contributed at the different joints during running and then try and see what's going on there?
Yeah, I guess. So if we took like from an NBC, or we just did, okay, we're gonna do a target torque of 52 at the ankle and a target torque of 29 at the.
Either, I think like either from the MVC or whatever, because then that would be more realistic, right? Like you're not doing 50% at the ankle and 50% at the knee while you're running.
Yeah.
So I'm wondering, could that be something you considered or you could do?
It could be something we could explore because it is different amounts of work and we're trying to look at what the energy cost is to do this different amounts of work. But this 52% and 29% comes from total leg work that is done during running. So we first need to capture total leg work that participant does during running and then break this down to what would that be at the ankle, what would that be at the knee, and then put that on the dynamometer. But the work that we achieve during running is like way more than what we can push on the dynamometer. So we would then have to do some sort of conversion estimates to get there.
And the reason I'm asking this, I was actually gonna ask a different question based on Brent's question, which was about the joint work redistribution and how many studies have shown this. So there's a lot of studies that don't show joint work redistribution with a prolonged run.
Yeah.
And I'm wondering, first of all, would you know or can you hypothesize why some have it and some don't?
That's a really good question. I actually have no idea
And
why we see that.
that
in
is
people.
really good. Question.
No.
No more than that.
Yeah.
Question.
So do you know how much of the work at the ankle was done by the passive components during running?
Mhm.
I assume you say their plantar flexor has much longer tendon compared to the hip flexors.
Yeah.
Knee extenders. So I assume during running, since there's a lot of energy returning coming from Achilles tendon.
Yeah.
Maybe that energy reduction efficiency is maybe because of tissue fatigue in the tendons.
Yeah, it could possibly be that. So you were saying like the tissue fatigue, that means that the strain on the tendon, the deformation would then slowly decrease over time. So we wouldn't see as much tendon deformation. Therefore, the muscles would have to shorten more, work harder to make up for this.
Yeah.
Yeah. Yeah, we could probably see. I guess I really need to look into this and I need to do more background research on the tendon work, but
I love it. Colin says that's what it is. He says it's viscoelasticity pre.
Yeah.
That's a speculation.
Wrong.
Yeah. Yeah, so I don't see why not in that. Cause I think we can sort of estimate tendon work based on our muscle fascicle, because we know what total joint work is. And we also know what the total muscle work is, and we know that muscle work plus tendon work equals joint work, so in that sense, we could estimate joint work. Or no, we could estimate tendon work, sorry, but we didn't directly put the ultrasound on it to actually see the strain differences in it, so that would have been cool to do.
Based on, like previous literature.
Yeah.
Just building off of Ashna's question, is there a difference when the speed is held constant, like for pre-post assessments versus self, like pace? And then I guess the follow-up would be, would we see a difference if cadence is held constant pre-post versus a change in like stride frequency, stride length?
Oh, probably. So Sano's study on the 10-kilometer time trial was at a constant speed run on a treadmill, and I believe Buchner's study was also at a constant speed over 60 kilometers. So during constant speed, Sano did observe this joint work redistribution, and I would assume maybe with faster speeds, we could possibly see it occur earlier in the run and maybe at higher magnitudes of distribution, possibly. And then what was the second half of your question? Oh, the cadence and the speed. Yeah, so I think the cadence and I'm gonna say like the flight time and the strike pattern definitely changes over the course of the run. And as you fatigue, maybe you don't the force you put into the ground isn't as high, because then your flight time is lower, and if you have lower flight time, that means your strides are getting shorter, right? So that could possibly get into the way of joint work redistribution, or it could be related to that in some way.
So we did actually a study where we had people run for 2 hours at a constant speed, and then at the end of those 2 hours for another, or maybe it was like not the 2 hours, so 90 minutes at a constant speed, and then the last 30 minutes at an increased speed. And then we only saw the joint work go up with the higher speed, but the redistribution didn't change at the faster speed as they fatigue. So we didn't see any of that redistribution throughout the run. But I don't know, like, also was the Sano study like level ground or uphill?
Level ground. Yeah.
Oh, it's good for those zones.
Yeah.
Anyone else that had questions for Lisa? This is your last chance. There we go. Awesome.
In the second part of the study, you did a direct comparison of muscles. Can you go over it again? Like, it's just a methodology question. Like, I didn't get back to it, I guess. Yes.
This one?
Yes. How did you? You did something different with the dynamometer, I guess, to
Yeah.
output the exact same amount of mechanical work from both joints, or?
Yes. So what we did is this 30 condition is 30% of the ankle torque and 50% of ankle range of motion. And this 40 is 40% of ankle torque and 50% of ankle range of motion. So now we're keeping the displacement of both joints the same. We're just increasing the torque. So in that sense, the displacement of the knee during the knee extension is the exact same angular displacement, so the exact same degrees as that of we're doing at the ankle during plantar flexion. All we're doing is we're just increasing the torque at which they need to hit. So in this sense, the work that is going to be done at the knee and at the ankle is going to be the same between the 30% in DC ankle and 50 range of motion. But when we increase the torque, work obviously increases because we're keeping the displacement the same between both of the joints. So in that way, we get different amounts of work by varying the torque instead of a joint.
Okay, excellent. With that, let's thank Lisa for her talk.